Okay, so the important stuff from Unit 3, okay, circular motion and gravitation. So very first day we talked about what it means to move in a circle, how circular motion is achieved. Okay, so basically the properties or principles of uniform circular motion. Okay, if something is moving with uniform circular motion, it is moving at a constant speed. True or false? True. Okay. An object undergoing uniform circular motion is undergoing accelerated motion. True or false? True. Also true. Okay, so how can it travel at a constant speed but also be accelerating?
Because the direction is always changing.
Right, the direction is always changing. The definition of acceleration is not a change in speed, it's a change in velocity. Okay, the magnitude of the velocity is constant, but it's always turning. Okay, and that requires a centripetal force, and thus a centripetal acceleration. Okay, so little things like that could easily be multiple choice questions. They test your understanding of the principles of circular motion. Okay, so constant speed, that's delta, so changing velocity, sorry for my shorthand. Okay, and we learned about some of these formulas. Okay, AC equals V squared over R, FC is mv squared over R, or mass times acceleration centripetal. Okay, so basically Newton's second law. Now, the other things we learned that first day were about period and frequency. Whoop, but I don't have them here, so we're going to talk about them. Okay, so we learned about period. Okay, period is the seconds for a cycle. Okay, or the time it takes to complete one orbit. Okay, seconds per cycle. Whereas frequency is cycles per second. Okay? In other words, T equals 1 over F. Okay? That is not a formula we use very often in this unit. Okay? So don't expect it to show up really all that much on this unit exam. It is, however, huge in the next unit. Okay? When we start talking about waves and simple harmonic motion, period, and frequency are like the two biggest things. Okay? All right. And we also talked about this formula. V equals 2 pi r over t. Okay? The way you calculate the velocity of something moving in a circular path. Okay? Basically, this formula is nothing more than d over t. Okay? 2 pi r calculates the circumference of the circle, okay? And we divide that by the time it takes to go around the circle one time. V equals d over t. Could you expect to have to use this formula somewhere on the test? Written response or multiple choice? I would say probably more multiple choice. It's a pretty simplistic formula. I'm not going to burn a 4-mark question on that formula. Okay, it is after all just V equals d over t. Okay, do you have to substitute that formula in some of the questions? Okay, that's kind of where it would come into the written responses if you had to substitute it into, oh, say a satellite question involving period and radius of an orbit or something like that. All right. The second day after we had talked about centripetal force, which is the force that causes the object to move in a circle and either pushes or pulls towards the center, okay, we talked about two different types of curves. And the first type of curve we talked about were unbanked curves, okay, where friction holds you in the corner. Okay, this is where we watched the Canada's Worst Driver slippery corner video, okay, where we saw that if you don't have sufficient friction and you do all the things that you would naturally want to do when sliding through a corner, okay, would result in less friction than you going straight. Okay. Do you suppose you might get an unbanked curve question on your written part of your exam? I would guarantee it, and I'm the guy who made the test, so. Okay. It was definitely one of the examples of uniform circular motion. What was the other kind of curve we talked about? Right. Bank curves. All right, should you expect to see one of those? I would. Okay. So unbanked curves, it's friction. Okay, but in a banked curve, it is the normal force, or rather, the horizontal component of it that keeps you in the corner. Okay, now you are not going to be required to derive that formula. Okay, I showed you how we derived it in class that day, but that formula is on your formula sheet. So you won't be asked to derive it, but it's important to understand how the bank curve works. Okay, so a bank curve is really just an inclined plane, okay, that goes around a corner. When we go around that banked curve, our inertia causes us to push on the corner more than we would if we were just sitting there, and that makes the normal force big. Okay? Its vertical component offsets gravity, and its horizontal component points back towards the center of the circle, okay? Acting as a centripetal force. Okay? Why are banked curves so useful? What do they do for us?
You don't have to use as much friction to stay in the turn.
Yeah, we don't have to rely on friction at all, actually, to stay in the turn. I mean, in the real world, we still do, okay? But there's essentially a guaranteed safe speed, okay, for an unbanked corner, okay, for a given angle of bank and a given radius. Okay, everybody with me there? So expect one of those as well in the written, and probably a multiple choice question about how they work. All right, after that, okay, there's more. Then we talked about artificial gravity. Okay. Now, is artificial gravity fairly straightforward? Okay, so we have a spinning drum, you're on the inside of the spinning drum, your inertia wants you to go tangent to the circle, but the inside of the drum prevents it. You push on the inside of the drum, what does the inside of the drum do? It pushes you back towards the middle and makes you feel like you have weight even though you actually don't. Okay, so that centripetal force, or normal force in this case, is going to feel like which force?
Gravity.
Gravity. Okay, which is why all artificial gravity questions are solved like this. Fc equals really Fn, but we want Fn to feel like the force of gravity, so we just plug in Fg. So there's not much to the manipulations, okay, for an artificial gravity questions. Fc equals Fg, and that's little fg, m times g, not the big one. Okay, if there's a mistake I see with artificial gravity questions, it's that people set it up and then it becomes a satellite question. Okay, as soon as you set it up where Fc equals big Fg, you're doing a satellite question, not an artificial gravity question. Okay, everyone follow me there? So it's little fg, m times g for an artificial gravity question. Okay, so as we were saying, okay, if you are standing here, according to my terrible diagram, okay, you are going to feel a normal force that feels like your normal weight, okay, and that's going to be providing a centripetal force, so m times g equals mv squared over r, okay, and you will provide artificial gravity that way. All right, that was like the first quarter of the unit. Okay, all of that stuff is uniform circular motion. Okay, the object going in the circle is moving at a constant speed. From there, we moved on to non-uniform circular motion, or vertical circular motion, where the speed now changes at various points because now gravity is involved. Gravity is slowing and accelerating throughout the entire circular path. Okay, the biggest thing we need to remember about any vertical circle is that Fc is the net force, and thus it is the vector sum of all forces. So forces in minus forces out will get me my vector sum of all forces. How many spots on a vertical circle did we talk about? 3. Okay, we talked about 3. Bottom on the inside, top on the inside, top on the outside. Okay, in which of those 3 can you feel weightless? Top on the outside? Anywhere else? Top on the inside, yeah. If I'm going at the what? Minimum speed. Remember, if you're on the inside of a loop, you have to achieve a minimum speed or you'll fall out of the loop. Remember, we watched Damian Walters run the loop. Okay, if you don't go fast enough, you'll fall out of the loop. Okay, if you're going just fast enough to stay in that loop, you don't push on the track doesn't push back, and you would feel weightless. if you're going over the top really fast, you will also lose contact with the track. You don't push on the track doesn't push on you, and you feel weightless, right? You are not actually weightless.
For the test, will we be marked if we draw the diagram of the circle? Is that a part of our givens?
It is not part of the givens, no. But if you wanted to, I would mark it as part of your givens if you drew it, but it's not like on your formula sheet,
Okay.
if that's what you're asking. Okay. But yeah, definitely, if you've got a vertical circular motion question, in fact, I may have put the diagram on there for it. Okay.
So this is on Monday, the test, right?
Yes.
Okay.
All right, where in a circle are you always, or sorry, where in the circle could you feel heavier?
At the bottom.
Anywhere else?
At the top.
At the top, inside or outside?
Inside.
Inside. Okay, going over the top on the outside, I'm always going to feel either normal, if I'm just sitting there, or lighter. As soon as I'm moving over the top, I'm gonna feel lighter. Okay, that's the only spot where I can never feel heavier, is going over the top. Okay, but if I'm going under the top, here on the inside, I could feel heavier. If I'm going faster than the minimum speed, I'm gonna, feel heavier. Okay, in that situation, right? If you're like riding a fast roller coaster, the top of a loop can give you lots of G-forces, not as much as the bottom of the loop, but it can still give you G-forces if you're going fast enough. Okay, I think I remember telling you guys when we used to go to West Ed, we had the guy use the SparkView app on his phone and just put it in his pocket for the mind bender. Okay? And when he went through the loops, he was registering 2.5 G at the top of the loop and 3.5 to 4 in the bottom. Okay, so you can still feel heavier than normal under the top or inside on the top of the vertical loop. All right, so the situations you might get there could be situations of apparent weightlessness, okay, or situations where you are quite a bit heavier than normal, okay, but in the end they all come down to forces in minus forces out, and there are the situations that we just talked about. Okay, if you're going over the top of the vertical circle, normal force acts out, gravity acts in, and if you go fast enough, the normal force will disappear. If you're on the inside, gravity acts in, normal force, if it's present, also acts in. There are no forces out on the inside top of the vertical loop. Okay, and then lastly, you could be at the bottom of the vertical loop where Fn, normal force, acts in and gravity acts out, and that is where you would always feel heavier. That covers about the first half of the unit. Okay, the second half of the unit is gravitation.
If the question tells us that the person is feeling like 3.5 Gs, we apply that to the Fn, right?
Right, because that's the force you feel. Okay, you feel your apparent weight, never your real weight. Okay, so if it tells you you feel this many times heavier than normal, that's your normal force. Okay, so normal is mg. 2 times heavier than normal is 2 mg. 3 times heavier than normal, 3 mg. Yeah. All right, then we moved on to gravitation. What things affect the force of attraction by gravity between two objects? Mass and radius, yeah, or separation distance. That separation distance is measured from where to where?
Center to center.
Center to center, important to remember that. Okay, so the force of gravitation is linearly related to mass. If I double the mass, I'll have twice as much gravitational attraction. But in terms of separation distance or radius, it is
Linear.
it's exponential, but it's inversely exponential. Okay? If I separate the two by this much and then I double it, they're 4 times less attracted to each other, or 1/4, okay, the gravitational attraction of the first situation. Okay, so important to remember that. Those are the kind of things that could show up in a multiple choice question, okay, testing your understanding. Okay, the other thing to remember is that the force of gravity is a mutual attractive force on each other. It is not of one on, like the big one on the small one. Okay, we sometimes simplify it to look that way, but the truth of the matter is that they are equally attracted to each other. Another thing that could possibly be in the multiple choice part of your test. Okay, I spoiled this the first day we went over it, but the way I'm gonna test it, sun, Earth, moon in some alignment. Okay, I will want you to calculate the net gravitational force on one of those bodies. Okay, how do we calculate net force? Vector sum of all forces. Okay. And the forces involved there would be the force of gravity and the force of gravity. Okay, just between the two different sets of objects. Okay, the next thing we went over was satellite motion. Okay, all satellite motion breaks down to Fc equals Fg, but this time big Fg. Okay, Newton's universal law of gravitation, Fg. Okay, you can solve any satellite motion question with that setup. Okay, remember the key words to watch out for that may try to play a trick on you: height, altitude, or above the surface. How likely is it that you will get a satellite question on your test that will require you to substitute? I like it. You know me. Yeah, you get me. I like that. Okay. Yeah, I would say it's 100% because, well, the other way is just a little bit too easy. Maybe I'm a nice guy, but probably not. Okay. I would say the chances are you are going to get one that is going to involve the substitution of 2 pi r over t, okay, in for v. And that's what this is all showing here, okay, doing all of that. Okay, so you end up with that substitution instead. Okay, now the stuff that's in blue here is actually for gravitational field strength, so ignore all that stuff in blue, okay? Is there ever going to be a situation where you're going to have to do this? Why is there never going to be a situation where you're going to have to do that? They're the same. Writing that is like saying, hey, world, 1 equals 1. Okay. The reason you're never going to have to write this is because that's what that is. Excuse me. Okay? That's what that formula is. The only reason I ever showed you those two formulas equal to each other was to show you how we derived or solved for gravitational field strength. Okay, so you will never have a situation where you need to set these two formulas equal to each other because it's already done for you on your formula sheet, because all that will happen is the smaller mass will cancel. Okay, and then you'll be left with the gravitational field strength formula. Okay, so we talked satellites. Okay, and satellites, anything that orbits something else. Okay, so moon orbiting the Earth, satellites orbiting the Earth, space probe orbiting Mars, planets orbiting the sun orbiting the center of the galaxy. Okay, whatever, as long as it's orbiting something else, it's a satellite of the central body. Okay, gravitational field strength. Okay, watch out for those. What's the other way I might say gravitational field strength? Acceleration due to gravity. Yeah, they are the same thing. They measure the same thing. Okay, newtons per kilogram and meters per second squared are acceptable units for
What's the other thing you said?
acceleration due to gravity. Okay, so that is what we use if we are anywhere other than the surface of the Earth. Okay, and like at the average Earth radius. Okay. You could get a question that says you're at the top of a very tall mountain on Earth. Well, then you're going to have to calculate the gravitational field strength there because the radius won't be 6.37 times 10 to the 6. Okay, or a tall building or whatever. Okay, some situation. Okay. And okay, you're not going to have to worry about Kepler's law of periods. Okay, there's one question on the test that you could solve with Kepler's law of periods, but it can also be solved with FC equals FG. Okay, and quite frankly, I'd rather you do it that way. Should you know Kepler's 3 laws? You should. Kepler is an important guy. Okay, he figured out how the solar system works. Okay, so law of elliptical orbits, law of equal areas, law of periods. Okay, make sure you go over those in your notes so that you could recognize them should you encounter a multiple choice question about Kepler's laws. You know, like which of the following would Kepler not agree with? Okay, find the 3 he made up and the one that he didn't. Okay, something like that. Okay, so the setup of the test is, and I think I've updated it since this, so I'm going to just tell you. All right, we are looking at 15 multiple choice questions. Okay, so 15 multiple choice questions asking about the principles of circular motion, okay, the types of curves, principles of those curves, because that's principles of uniform circular motion, principles of vertical circular motion, universal gravitation, satellite motion, curves, principles of circular motion, Kepler, gravitation, principles of circular motion, gravitation. So it's lots of the same, just okay, worded differently, testing something just slightly different. Okay. And then you have a written response section with 8 problems. Okay, and the written part is out of 33. So this is by a considerable margin your shortest test. Okay. All right, written response. Unbanked curve. I already told you this, but I'll go over it again. Unbanked curve. Okay, bank curve. Vertical circular motion. Satellite motion. Gravitational field strength. Universal gravitation. Artificial gravity. And a second vertical circular motion problem. Okay, so 8 written response items. Judging by how long it took me to make the key, I really don't think time is going to be a factor. I was done the key in 13 minutes. I almost put a 9th question on. Okay, it's short. Okay, now I'm not saying that the questions are easy. You've seen questions like every single one that's on here, and you've done well on them thus far. Okay, but don't walk away from today and go, oh, Coderre said the test is super short, so I don't need to study. Coderre never ever says that. Okay, Coderre says this is an opportunity for you to raise the exam portion of your mark, which can significantly change your overall mark for the better. Okay, so if you are well prepared for this test, it is a big opportunity to change your mark for the better. Okay, and that's good at the end of May. Finals are coming up. And they're not usually a good opportunity to raise your mark. Okay? Not that it doesn't happen sometimes, but usually people do about the same on the final as they did in the course. Okay? Rarely do I have anyone do significantly better or significantly worse, really. Okay? All right, questions from you guys? Would you like me to go over in a little more detail or demo?
Could you go over a question with like the moon, sun, and Earth, where you have to find a net gravity, or the net like force of gravity?
Oh, I these questions and I don't have a single one about that. Okay. Not drawn to scale.
Okay.
Okay, so we've done basically all the situations to do with this one already. Okay, so I want to calculate the net gravitational force on the Earth due to the sun and moon. Okay, give you about 3 minutes, it's probably about all you need. It's 3 calculations, 1 calculation per minute. Okay, so for this question we have 3 calculations. Force of gravity between the Earth and the sun, force of gravity between the Earth and the moon, and the net force calculation. Okay, so force of gravity between the sun and the Earth, 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, mass of the sun, times 5.98 times 10 to the 24, mass of the Earth, over 1.50 times 10 to the 11 squared. That's the Earth-Sun distance, center to center. Okay, when we do that, we should get 3 point, I don't remember what it is. Done it enough times, I should remember. Okay, 6.67, negative 11, 1.99. Divided by 1.5. All right, so 3.53 times 10 to the 22 newtons. Okay, toward sun. All right, then I got to do the same calculation for the Earth and the moon. Okay, so force of gravity, me, moon and Earth. Okay, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, mass of the Earth, times 7.36 times 10 to the 22? No, 20. What is it, 20, 22? 22, right. Okay, and then divided by 3.85 times 10 to the 8. Is that right? Yeah. All right, and that number has to be squared. That comes out to 1.99 times 10 to the 20 newtons, I think. Or is it 1.98? Sorry, it's close enough. Okay, so we've got those 2 numbers. Now I got to find the net force acting on the Earth. This one's towards the sun. This one's toward the moon. What do I need to do with those numbers? Subtract them. Okay, now if there was a different orientation, I might be adding, or I might be putting them tail to head and finding the hypotenuse of the triangle. All depends on where I stick the moon, okay, in the question on the exam. Okay, so in this case, I would subtract them, and I think it comes out to 3.51, okay, times 10 to the 22 newtons towards the sun, because, of course, force is a vector quantity. I would need to have a vector there. Okay. What else?
Could we do one of those, another question where you have to substitute 2 pi r over t for v, or 4 pi squared r squared over t squared?
Okay, there you go. There's a substitution now. So we are looking for the period of a satellite. What are my units going to come out to? Seconds, is that okay? Totally okay. Unless they specify otherwise, we'll leave it in seconds. Okay, we had a question on the quiz that specified it wanted it in hours, so we had to convert. Okay, unless it actually specifies, leave it in seconds. All right, so we're looking for the period of a satellite orbiting Earth at an altitude of 2 Earth radii. So here's Earth. The satellite is 2 Earth radii from the surface. What do I want? 3 Earth radii, because that's how far it is from the center. Okay, so the radius that we're going to use here is going to be 3 times 6.37 times 10 to the 6. And little things like that are the kinds of dirty little tricks, okay, that come up on tests. For people that are paying attention, they're easy, okay, but if we're not paying attention, they're the kind of things that can kind of jam us up, okay? All right, so we're looking at 1.911 times 10 to the 7 meters. Okay, so it's a satellite, so FC equals FG, right? We're going to do the substitution, okay, where we have m 4 pi squared times r over t squared equals big G times the mass of the Earth times the mass of the satellite over r squared. The mass of the satellite is going to cancel as it always does, and now I'm trying to find the period. So I'm going to multiply both sides by t squared, multiply both sides by r squared, and then divide both sides by big G times the mass of the Earth, and square root to get t. Right, so t is going to equal then, okay, the square root of 4 pi squared times 1.911 times 10 to the 7 cubed divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Yeah, but I didn't put another one here, and I should have, so it does the bottom. And then one more bracket. Or not? Nope. No, that can't be right. What did I mess up? Oh, I forgot to cube it. That's what I messed up. Second entry. Go back here. That's better. Okay, so we got an orbital period of 26,281 seconds, but I think we had no significant digits. 3 Earth radii, I guess that would be, well, 2 Earth radii, 2 might be a measured value. Okay, so it'd be 1 significant digit. But no, because it was a factor. So, as many significant digits as you want on that question. 26,281.9 seconds. All right, that one makes sense. Okay, what else? I did post the unit exam review package on Friday, so it's in the stream. There's a review sheet and stuff there.
We do a bank curve.
Bank curve, yeah. Okay, there you go, bank curve. Okay, so we're looking for the speed this bank curve can be negotiated at. We know what theta is. We know it's 16 degrees. Okay, we know it has a radius of 70 meters. Okay, what if they said it's a 70-meter curve? It's also the radius. Yeah. Okay? We never describe a curve by its circumference unless they outright say the circumference of this is. Okay, but they say it's a 70-meter curve. That's the radius. Okay. All right, and we're looking for the speed at which it can be negotiated. So tan of theta equals v squared over r times g. It's our bank curve formula. Okay, so we're solving for v, so we multiply both sides by r times g, and then we square root to get v. So v would be the square root of 70 times 9.81 times the tan of 16. What mode does your calculator need to be in?
Degrees.
Degree. I know on the circular motion assignment, a few people lost marks on the 2 bank curve questions because their calculators were definitely in radian mode. Okay, because I looked at the answer, the work was all 100% right, and they had a ridiculous answer. Okay, and the only way that they could get that answer was if their calculator was in radian mode. So make sure, especially if you have math this semester, that when you come to physics, you put it back in the right mode, I mean degree mode. Okay, all right. So for this one here, square root 70 times 9.81 times the tan of 16. So 14 meters per second.
So a question like this would only be worth like 3 marks.
That'd be a 4-mark question. Yep, because you get 1 for your givens, 1 for identifying the type of question, 1 for your algebra, 1 for your answer.
Yeah.
Okay, what else?
Can we do a roller coaster question?
Like a vertical loop?
Yeah, vertical loop.
Not that one. There you go. It's not a roller coaster, but it's a vertical circle. Okay, so if we're going over a rise and a path, we're going over the top of a vertical circle, okay? That means this is what would happen generally, except in this question, they tell me that my tires lose contact with the path. So what happens to my normal force now? It becomes 0, right? I would feel apparently weightless because if I don't touch the path can't push on me. Okay, so now we're dealing with a FC equals forces in minus forces out. Well, there aren't any. The only force out is 0, so there isn't a force out. Okay, so we're left with this. FC equals the forces in. So that means mv squared over r equals m times g, and we're looking for v. Here's that thing again. Right? Okay, so v equals the square root of 10 times 9.81, so whatever the square root of 98.1 is.
9.90.
9.90, Okay, so tomorrow we will be starting Unit 4, Simple Harmonic Motion. We'll be talking about pendulums, masses on springs, and I'll bring out the ghetto pendulum again. Okay, this is awesome.